Welcome, everyone, and good morning. It's been an exciting year for NVIDIA. We've spent over $2 billion on AI research and development and brought you amazing new technology, which I'll talk about today. We managed to put over 5,000 CUDA cores in our latest Tesla V100 GPU to process deep neural networks at an amazingly fast pace. And there's only one thing that we forgot to do, is figure out how to get 3,000 of you in the convention center at COEX in a short period of time. So thank you for all of you who had to wait in line, and we'll work on that for next year. As an engineer and a computer scientist, this is an amazing time in the history of computing to be working in the industry. There are three amazing forces that are shaping the future of computing. For over 50 years, the force known as Moore's Law, doubling the number of transistors every 12 to 18 months, has propelled computing forward. This has been not only a law or a statement about the capabilities of computing, but it's also represented the demand for computing. Now, unfortunately, all major processor vendors are coming to the point that Moore's Law is ending. Moore's Law is ending not that there are not more transistors. We saw several new processors announced this week that doubled again the number of transistors. Yet the performance, the single-threaded performance, has not improved, perhaps no more than 10% a year. Meanwhile, the demand keeps on going up. And in fact, the demand is rising at a super Moore's Law, not doubling every 12 months, but growing 20, 30, or 100x every year. And NVIDIA, with GPU computing, is continuing to meet this demand curve. The reason is, of course, not because NVIDIA has faster transistors than other companies. The reason is because of the core architecture of the GPU in accelerated computing. Using the CPU that ships with every NVIDIA GPU to run serial code, and then saving the parallel code for the GPU. And in fact, today, this architecture is being copied not by several new companies, but by literally dozens and dozens of new AI chip startups that are working to build accelerated computing solutions. And the reason from some of the largest computing companies in the world to some of the newest startups building AI chips is because of the new way that software will be written. For all of my career, and even long before, computer scientists around the world went to school and they learned to write if-then-else code. Computer programming, as we know it today, written by humans. And there's only one problem with traditional computer programming. Even if every human in the world learned to program, there are not enough people to write code to manage all of the big data that has been amassed in public, in private, in hybrid clouds around the world. Deep learning, in the deep learning revolution, has addressed that. At its core, deep learning is software that writes software. We no longer need computer scientists to be able to write if-then-else code. What we need is computer scientists and data scientists to take data, take deep neural networks, and use the deep neural network technology to write the new software. And there's one other thing that you need to make this possible, is you need a supercomputer to actually run the deep neural network training. So what is NVIDIA in this new market? NVIDIA, of course, is known for our wonderful accelerators that have met demanding applications from PC gaming to high-performance computing and deep learning in the data center to inference and applications on the edge, such as robotics and autonomous vehicles, self-driving cars. And the way we've done this, though, the way we have created a super Moore's law is not simply by building great hardware. It's by building complete platforms, the hardware, the CUDA development environment, libraries like cuDNN, which are built into every framework, and a complete stack all the way up to rack level and DGX pod level solutions, a data center blueprint for the software of the future. So let's go through today in a few topics that I'll cover, so I'll have to speak quickly. Deep learning is now everywhere. If you have a Samsung phone and you use the Bixby assistant, or if you have an iPhone and use Siri, if you use Naver Maps or other mapping programs, almost everything you do as a consumer today, the software has been written in part by deep learning running on GPUs in the data center. But today, we see deep learning coming out of the internet and going into new industries. Medicine and biology, media and entertainment, where for many years the GPU has been used by graphics. And we'll give you a bit of an update later on what we're doing in graphics. But the new graphics are again being aided and being written by AI programs. Intelligent video analytics. No doubt from when you left your home this morning to when you entered the convention center, you walked by many, many, many cameras to help make this a safer city. The question is, how many of those videos were being analyzed in real time? Is this possible today with deep learning? And finally, we'll give you an update on transportation. We have a little home movie of our own self-driving car, which we'll review. Now, of course, Korea is an amazing country for technology innovation, and Korea has not stood still with the AI revolution. There's many great examples. SK Hynix, one of the largest semiconductor vendors in the world. Their memory probably exists in many of the devices or laptops or computers that you own. They use deep learning to inspect chips, memory chips, coming off the assembly line. This previously had to be done only by humans. By adding deep neural networks in deep learning, it can improve the accuracy of the inspection, lower the number of false positives, and end up with a higher quality memory product that comes to your device. Now, deep learning has been around for many years. If you do research on deep learning, you can go back 30 or 40 years and see some of the first deep neural network research papers that were written. And big data has been around for 10 to 15 years, as Google, Amazon, Microsoft, and others amassed huge amounts of online data. But it wasn't until 2012 when the first deep neural networks were ported to CUDA, to the GPU, that deep learning was enabled by NVIDIA hardware. But let's take a look at what is happening to the demands. As deep learning has become more popular, there's been more and more research. This year alone, over 6,000 new papers will be published in the top 5 AI conferences talking about new types of deep neural networks. From the original AlexNet in 2012, state-of-the-art image networks, such as Inception v4, or today require 350 times more compute power. That is a super Moore's law curve. And when CPU performance is increasing at 10% a year, how do you get 350 times, not 350%, 350 times more performance? It's through that accelerated computing, GPUs, plus the full solution. And across other different types of deep neural networks for speech and for translation, the same is also true. So how did NVIDIA solve this? Today, the Tesla V100 Tensor Core GPU is the world's most powerful processor for deep learning and for high-performance computing. You have over 5,000 CUDA cores delivering 7.5 teraflops of double precision performance. However, for deep learning, new algorithms have evolved that use mixed precision performance. And for this, we built a special new architecture inside the GPU, the Tensor Core. And because we build the world's largest processor, over 21 billion transistors, we're able to fit not only the CUDA cores, but the Tensor cores and other specialized logic. The Tensor Core, just to remind you, solves this very simple math problem. D equals A times B plus C. Now, what makes it not quite so simple is A, B, C, and D are all 4x4 matrices. And they may be of mixed precision, 16-bit or 32-bit. Now, late this summer, we introduced a new GPU architecture, Turing. On the deep learning side, Turing was specifically focused with an improved Tensor Core, improving on the lessons from Volta for inference. If deep learning training is the software that writes software, once that AI software is written, executing or running the software in inference applies different optimizations. And so let's take a look at some of the optimizations we did with Turing. Our earlier Pascal GPU had FP16 capabilities. But let's look at how it compares to Turing using not only FP16 with the Tensor Core, but int8 and a new int4 capability. So instead of Pascal processing a single inference, at the same time, Turing with int4 can process over 32 times the amount of work. What this means is as more and more deep learning applications move into production, the cost of inference, the cost of running that software will continue to go down. The more Turing GPUs you use, the more money you will save. And again, we've worked across the board with many benchmarks in many different applications. Of course, image, speech, video, and natural language processing. And you can see here the wonderful gains in performance over the Pascal GPU, which in and of itself was an amazing platform. Now, of course, raw hardware horsepower alone is one thing. But to optimize it, you need software. Now, in the world of deep learning, there isn't just one development environment. TensorFlow has, of course, been made very popular by Google, but there are many others. MXNet, Microsoft Cognitive Toolkit, PyTorch, the list goes on. TensorRT is an optimizing inference compiler. The way to think about it is if you wrote if-then-else code, that's not what you executed. You would compile the if-then-else code to get the best performance. The same is true with a deep neural network. The deep neural network is writing a computational graph, and TensorRT compiles or optimizes that computational graph. And of course, because NVIDIA not only makes the GPUs for training, but we make a number of different platforms for inference, NVIDIA is best suited to optimize and know how to optimize that code for different GPUs in different execution platforms. Now, when we started with TensorRT several years ago, we thought it was a great advance, and it was. But it turns out, with so many new applications across the enterprise, across the cloud being developed, customers don't want to deploy a new GPU or a new rack of GPUs every time they have a new model that needs to be deployed for inference. And so a TensorRT inference server is not hardware server, it's a software server. It's an application that runs on the GPU, and it runs many deep neural network inference models. And so this allows you to take one GPU or to take a full rack or a full data center full of GPUs, and with Kubernetes, with NVIDIA Docker, with our NVIDIA GPU Cloud software, lets you manage that entire data center and make the most efficient use of the GPUs running multiple models. So the choice is yours. On training, everyone today is essentially using NVIDIA GPUs. As people started in inference, people thought, well, we have a lot of CPUs in our data center. We can just use those. Of course, as you add applications, you have to add CPUs. And so you could add a full row of computers, CPU servers, or you could add a single rack with a single server with our new Turing T4 GPUs and have the same effect. Less power, less space, less money, and higher performance. So the choice is yours, and if you visit the NVIDIA booth out in the lobby after, we have a number of different examples of inference running. Now, of course, 25 years ago when NVIDIA was founded, we were founded to build amazing computer graphics. And computer graphics continues to accelerate on a super Moore's law curve as well. So let's take a look at some of the things that we did to make that possible. With Turing, in addition to the updated Tensor Core, we added a brand new type of core for graphics called the ray tracing or RT core. Ray tracing has been the holy grail of computer graphics since it was first defined approximately 30 years ago. But ray tracing in real time was never possible. When someone wanted to do a motion picture or a production video, they would use hundreds or thousands of CPUs running for days or weeks to ray trace and render the film. Turing does the same thing for ray tracing that the tensor core did for deep learning. It makes it possible now in real time for the first time to deliver amazing ray-traced graphics. Now, because Turing has the tensor core, besides just the new ray tracing power, there are all sorts of new deep learning algorithms being applied to make better graphics. Deep learning can colorize an old black and white movie. Deep learning can take a video stream that perhaps is noisy. There was low bandwidth on transmission, or there was some error in transmission, and it can now remove the noise and make the image look as good as new. If you have an old painting where you have parts were torn away, with in-painting, a deep neural network can recreate the missing data. And with super resolution, you can take an image that was captured at lower resolution and make it look like the camera was immediately a foot away from the image with super resolution. Again, the Turing GPU, with the ray tracing core for graphics, the tensor cores for inference, lets all of this run on the same GPU. Of course, some amazing performance numbers compared to its predecessor. But talking about graphics doesn't mean anything compared to seeing it. The old saying, a picture is worth 1,000 words. So for the 70th anniversary of the Porsche 911, and I know in Korea, in every country, people have their favorite cars and people love cars. Porsche designers are thinking of building a 70th anniversary edition. This car has not been built yet. Now, normally what a car designer does is they build a clay model, they build some computer models of it, and they would take those computer models and they would put them on a large cluster with hundreds of CPUs and render or fill in the color. This takes perhaps overnight or a day or two to do, and the end result then is a beautiful short video clip. The problem is, if the designer says, well, what if I change the color, or what if I change the lighting, would the car look different? I'd really like to see it from a different angle. Then they have to go and wait another day or two. So with our Quadro RTX GPUs, Turing with the new ray tracing cores, that overnight or over several day process can be done in real time. You could take this beautiful car model and the director could say, change the lighting, change the color, spin it around and look in the back. Now we can't actually show you this here, but we can show it running in real time. Again, down in the booth, we have this demonstration. But let's roll a little video and show an example of what you can do in real time, not in a video.
The speed of light, a universal constant, never diminishing, never ending. 70 years of unrelenting progress. The Porsche 911 Speedster concept. The speed of light.
So you can go down to the NVIDIA booth. You can see this Porsche in real life, spin it around, change the color. But you can't buy one. But what you can do is you can place your order, I believe, downstairs for a Quadro RTX card so you can design your own Porsche in real time. So Turing's a giant leap for PC gaming, for ray tracing, and for inference in the data center. Before there was deep learning, NVIDIA GPUs and CUDA were famous for accelerating science. And with every generation of GPUs, scientists around the world find amazing new science to move forward. Today, of the top 15 applications that use the most computer power in data centers, high-performance computing data centers around the world, all 15 can run on a GPU. And in total, there's over 600 accelerated applications for science that run on the GPU. So one has to ask yourself, if you're running a high-performance computing center at your university, at a company, and you're not using GPUs, what is that costing you? And how much could you save if you're running VASP or GROMACS or AMBER or LAMPS or any of these other codes, and you had a GPU saving you money? Now, it's not just NVIDIA that thinks this. In the US government this year built the world's fastest supercomputer. In the past, or other supercomputers have tens of thousands of servers to build the supercomputer. This system has only about 4,000 servers, but in each server, there are 6 V100 GPUs, a total of over 27,000 systems. The first supercomputer in the world to break the 100 petaflop of double precision performance, and actually capable of 3 exaflops of deep learning tensor operations per second. There's been a number of different papers and talks given that you can find on the internet on Summit. Now, as I said, it's been a very busy year. And of course, we built not just the world's fastest supercomputer, we built the second fastest supercomputer in the US. We built the fastest supercomputer in China, in Japan, ABCI. We built the fastest supercomputer in Europe, PISDAINT in Switzerland. And of course, not only governments buy supercomputers, large companies do. And so we built the largest commercial supercomputer for Eni, the Italian oil company. Now, you may notice that absent from this list is any Korean supercomputer. So it's not an omission, they just aren't there. So we would be very happy, and EJ, who gave the introduction, would be very happy to work with Korean supercomputer centers and the Korean government to build a large supercomputer here in Korea that next year we can put on this list and join 17 of the world's 20th most energy efficient supercomputers. Of course, science in all those applications on the GPU, since we developed CUDA back in 2006, have been focused on computational science, simulating the laws of physics. Now, the laws of physics, we don't think they're going to change anytime soon. So we think that investment in accelerating high-performance computing apps is very worthwhile. But even building the world's largest supercomputer, there's many times where it still isn't powerful enough to simply rely on the laws of physics to solve the problem. You often don't have all the information you need. You're missing information. So you need to run simulations. Simulations are very time-consuming. But with the advent of AI, there's a lot of smart people in all these supercomputer centers. They've said, how can we apply data science to steer our simulations, maybe not have to simulate parts of the code because we're smart enough with AI to pick? And when we do simulations, how do we do them more accurately? And together, AI plus high-performance computing is becoming a new instrument of science. There's many examples from national labs and national supercomputer centers around the world where even starting with a GPU-accelerated supercomputer, by applying artificial intelligence as a transformative tool, they've been able to accelerate their science, get results 20, 30, 50 times faster. Now, not every one of those 600 applications work with AI today. In fact, even of the top 15 applications, not all of them work with AI. Some of them will continue to be compute only. But you have to ask yourself if GPUs are good for accelerating high-performance computing and AI is being used in high-performance computing, then why would you ever build two separate systems, right? It wouldn't make sense to build one system with one technology for your high-performance computing and another system with a different technology for your AI and have to move the data back and forth. And so again, this is the power of GPUs. There's a number of companies doing high-performance computing in AI here in Korea. This comes from a very small startup, SI Analytics. I met with them last night. And again, they're using AI to accelerate the processing of satellite images. Let's say there's a flood right here in Korea after a big rain. Well, that will get captured by aerial images. And in the past, well, it took SI Analytics 40 minutes to analyze that image, right? And if there's rain across the country, you might have 5 or 10 or 20 floods. So how long does it take to analyze that data to then go and tell the police or the fire department where to go when there's a natural disaster? It takes too long, right? With SI Analytics' new AI-based software, they can take that 40 minutes and shrink it down to only 3 minutes. So the next time there's a natural disaster, the next time they're analyzing crop yields, doing anything else, they can do it over 10 times faster. So again, the Tensor Core GPU fusing HPC and AI for the first time ever gives you a single architecture, computing architecture, that you can solve two of the largest problems of computing today, HPC and AI. Breakthrough performance, some other examples. And a great example again here from LG. The CNS division of LG is using deep learning for image inspection. Here inspecting not only computer chips, but LG, of course, makes all sorts of things, from little computer chips to very large mechanical devices. And by improving the accuracy of inspection, it means that it lowers their cost of production. And as you buy as a consumer an LG product, you're getting a higher quality product. Again, thanks to NVIDIA GPUs and deep learning. So again, the choice is yours. You can fill your data center with CPUs. The power company maybe likes this until they run out of power, right? And then you can't add any more CPUs. Or you can replace that with a single rack, not even a full rack, and save money. So as our CEO says, the more GPUs you buy, the more money you save. Now, how about data science? We talked about high-performance computing. We talked about deep learning. But deep learning is only a small part of data science. There's a very large part of computing that is data science, that is machine learning. And unlike deep learning that has been around only since 2012 in practice, machine learning really builds upon technologies that are much, much older. In fact, the data science platform starts like this, going back all the way back to the invention of Python. Python is so dominant that my son, who was a computer scientist in school, had a friend of his, a young woman, over for dinner. I live in California by NVIDIA's headquarters in Silicon Valley, and it's next to Stanford University. Stanford is a very famous university, maybe not quite as famous as Seoul National University, but they start with the same letter. And this young woman was starting her PhD this year in molecular biology at Stanford. So I always love to have young women over at the dinner table that are getting their PhD in molecular biology. And she talked about, she goes, yes, of course I use GPUs, I use GROMACs, I use LAMPs, many of those codes that are there. And after dinner, I noticed my son was teaching her Python, going through Python. And I said, well, you're going to Stanford as a computational molecular biologist. Why are you learning Python? And she said, well, school starts next week, and the first day of school, we have to take a test in Python and be able to pass. So if you're a new biology PhD student at Stanford, you have to know Python. Now you might say, why? If AI is software that writes software, why do you need to learn Python? Well, in data science is more than just deep learning. And in fact, is you see here, NumPy, written right about the same time as CUDA, let you not only write simple programs in Python, but let you deal with large array, multidimensional array types. Pandas, written in 2008, let you do data analytics in Python. And in 2010, NVIDIA built scikit-learn. If you talk to any computer science student anywhere in the world that has gone to school, graduated in the last 10 years, they know Python for sure. And if they took any data science class, they know pandas and scikit-learn. And what a data scientist does, what a biologist does, they get a lot of data, DNA data, cell data, experiment data, and rather than writing if-then-else code for it, before deep learning, they used machine learning, using pandas, using scikit-learn. What is the average temperature compared to the red blood cell count compared to what disease they have? And they do data science. And for years, this only ran on CPUs. But of course, as big data grew, running this on CPUs alone became slower and slower and slower. Matthew Rocklin invented Dask. Dask was a language that let you take that machine learning that became too slow for one server and run it on many servers. But that helped a little bit. It helped to get to 2 or 3 or 4 servers, but the challenge is it didn't help that much. And so in 2016, the start of GPU accelerating machine learning occurred when Wes McKinney developed Arrow. Arrow is a universal data frame, a data format for machine learning. And we worked with Wes, and it was developed with a GPU in mind. Even though all that other code, the pandas code, scikit-learn, didn't run on the GPU yet. And this year, we finally announced Rapids. We've been hard at work, like I said, spending $2 billion this year. And Rapids takes all of the machine learning algorithms like nearest neighbor, XGBoost, other machine learning algorithms, and it implements GPU-accelerated versions of what pandas and scikit-learn do. And so let's see what happens when you take data science in machine learning and move it from a CPU to a GPU with Rapids. Now, in data science, there's two steps. There's the ETL, you're extracting, translating the data, right? The biology student at Stanford is pulling data from many different databases. She needs to transform it into a common format before she can do her machine learning. She can run up to 20 nodes, and the performance looks okay. But the problem is the ETL, translating the data, it speeds up as you add more CPUs. You can divide the problem, and at 100 CPU nodes, it starts to slow down a little bit. But the machine learning doesn't really speed up. Notice from 20 to 50, it just speeds up a little bit and almost doesn't speed up at all, going from 50 nodes to doubling the hardware. The problem is, and why you say, how could you add more computers and it doesn't speed up? Well, if you're doing all those sort of comparison math, every comparison has to run not just on the CPU and do math, but it has to talk to all of the other CPUs over the network. So in effect, you just can't add enough CPUs to make it run fast. And so DGX2, NVIDIA's largest server, again, cuts that to a fraction of the time. And so let's talk a little bit about what does that do to the life of a data scientist. Now, I asked one of my engineers, this looks like something my son, well, if my son would have written this, it might have had more misspellings. The NVIDIA engineer only misspelled a few words. See if you can find the misspelled words. But I like this picture so much that I kept it. A day in the life of a data scientist. They come into work, they start their ETL running, they go and get some coffee. Notice the coloring. And this is one of my engineers that did this graph. They said that when he's getting coffee, it's green. Good, I guess, for the engineer. Lots of time to wait. Now, if it's my business, I don't think it's good if the engineer is spending all that time getting coffee and waiting for the CPUs to run. It should be the other way around. And in the red, in the first chart, is where the engineer is actually working and thinking, right? And then they have to wait again. Switch to decaf. Decaf is misspelled. Don't go home and spell it this way. One F only. And then, of course, he has to work late because he doesn't get done in time because he convinced you to buy him another 50 CPU nodes and it didn't run any faster. So that's a problem. But now if you take this code and move it to Rapids, and the beauty is this is very easy to do. You can do it in a matter of a few minutes or a few hours because it's not you have to learn TensorFlow to use deep learning. It's the same exact pandas code, scikit-learn code, only with the NVIDIA Rapids software libraries underneath. So now, look at the graph. A lot of red. The engineer doesn't get much time to get coffee, so I guess it's red. But really, that's useful work, the red work there. So again, we made Rapids completely open source because there's 10 years of machine learning code out there. We've taken some of the most popular algorithms and ported them in Rapids. There's still a lot more work to do, but there's a lot that you can go and start with today. So come down to the booth, learn a little bit more about it, and if you're doing anything in machine learning, would encourage you to run this. DGX2 is, of course, our fastest platform for running Rapids, but you can start with any NVIDIA GPU. And again, it's all about how much memory and the size of your data set. How do we scale it? And why is DGX2 such an amazing platform for rapids? We have a DGX2 down in the booth. It's very big. It's very heavy. It is 165 kilograms. We are not worried about anyone picking it up during the show, during the keynote, and walking out of the booth. It's too heavy. But besides 16 GPUs, the real innovation in DGX2 is that it connects all of the memory in all of the GPUs using NVLink. And it, in effect, creates the world's largest GPU, 512 gigabytes of memory. And the little piece of circuitry that makes this possible is NVSwitch. So this is to scale. It's this skinny little chip. And you might think, most of the computer chips I've seen are square. Why did NVIDIA do a skinny little chip? It doesn't seem to make sense. Well, it's a switch that goes inside the computer. And think of a network switch, right? If you've been in a computer room, you see the network switch. It's not a big fat server, it's a very thin switch. And the reason that a network switch is thin is the same reason that the NVSwitch has this chip, has this shape. At the core, it's really just a crossbar that connects up to 18 different NVLink connections. So any NVLink can talk to any other NVLink, and thus the GPUs and their memory can talk at full speed across the switch. So it's a very small switch, but it's very, very powerful. So again, for machine learning, this would be your traditional CPU-only data center. And with DGX, you get this. So again, it's really up to you. You can spend a lot of money and buy CPUs if you have the power, or you can switch and buy GPUs. And by the way, once you buy one DGX2, most of our early DGX2 customers have now come back and bought more because they realize the more you buy, the more you save. So with Rapids, NVIDIA now is able to accelerate all of the major workloads in a modern data center. Science and technical computing and high-performance computing, deep learning training, deep learning inference, and finally machine learning. The last major workload that the GPU did not accelerate. But of course, not every computer will be in a data center. Not only has AI come out of the large internet service providers and into industries, AI has come out into the real world, into robots, into automobiles. Your car in the future will be a software-defined car. I was talking to some of the Porsche autonomous vehicle team, and they said, well, at Porsche, people buy a Porsche because they like to drive. Our car will be autonomous for safety reasons, but we're still going to have the steering wheel because we think people will want to drive it sometimes. I think that's a German sometimes opinion. I think culture in Asia, sometimes you don't want to drive the car in the traffic here. I've driven in the traffic in Korea. I like not driving. NVIDIA Drive is our software that makes autonomous vehicles possible. Now, I get asked all the time, well, when do you think that I'll be able to buy a fully autonomous car? I know some car companies have that option, it says fully autonomous, but the cars that you buy today are not really fully autonomous, at least not on any road under any condition. There's still a lot of testing that needs to be done, and there's still more software that needs to be written. Only, of course, that software is not being written by humans writing if-then-else code. In fact, NVIDIA uses over 1,000 DGX servers to write our autonomous vehicle software. And so because we have maybe more DGX systems writing software than any other car company, arguably, I believe we've been able to produce better results. This is a little loop that our self-driving car did. 80 miles through the freeways, or 80 kilometers through the freeways of Silicon Valley. 4 large freeway interchanges, multiple lane changes, and at no time was there a disengagement. In no time did the driver have to put their hands on the wheel or the brake. By the way, all of our self-driving car test cars have, of course, a driver in them, and they have a safety co-pilot. We always drive with 2 people on the road. So you may see in the videos, sometimes the safety pilot is in the back seat filming, but they have that stop button that they can hit. So let's go ahead and run the video. NVIDIA, of course, doesn't make the car itself. We use a standard car, but there's the NVIDIA offices where we started, and you can see it driving. So staying in the lane on a freeway. That's Highway 280, I believe. We're tracking all sorts of different vehicles. Because we have a bounding box, we can tell, well, this is a pickup truck. I know that's not too popular here, but in the US, pickup trucks are very popular. SUVs, cars. Of course, you need to understand the difference in the vehicles. If you look carefully, you can see the NVIDIA chase car behind it in some of the scenes. We're mapping the lanes. Different lanes are different colors. Again, changing through an intersection. We're doing path planning. So the car is deciding by itself it should change lanes. I don't want to go off this freeway. I want to stay on this freeway. We not only use AI outside the car, we're using AI inside the car. Right? We can tell if a driver is not paying attention.
What's the weather in San Francisco now?
The weather is 67 degrees and cloudy in San Francisco.
How about tomorrow?
There will be partly sunny skies with a high of 69 degrees and a low of 58 degrees in San Francisco tomorrow.
There's some other examples of also doing the path planning. Where is it safe to drive? Where is it not safe to drive? Perception, of course, recognizing over 100 classes of objects. Again, changing freeways here. No hands on the wheel. Again, notice cars cutting in and out in front of the vehicle, and it's not a problem. We're also have cameras looking behind. Well, this is obviously from the car behind. And now we're getting back to our headquarters. 80 kilometers, 50 miles, no hands. So that's a little progress report. And next year I look forward to being here and giving you an update. I'm sure we'll be going more than 80 kilometers then. What makes all of that possible is, of course, our new Xavier processor, the world's first autonomous machine processor. With the automotive use case, it's packaged in our drive hardware, but there are many other autonomous machines besides automobiles. This is a system on a chip. So I was correct when I said every GPU works with a CPU, but sometimes that CPU is inside the same chip, an entire system on a chip. Again, 9 billion transistors. And this, of course, does not just have your CUDA cores and your ARM cores a number of specialized processors, vision processors, a DSP, and our own deep learning accelerator, which we've open sourced the hardware to. So if you don't need an entire Xavier chip, if you want to do a little watch or a little $5 sensor that runs inference, you can download the source code to DLA and integrate it into your own chip.
Attention.
Another few examples there of inside the car monitoring. Now, after automobiles, the next most interesting use of Xavier is in robotics. And in a certain sense, building a robot, not the type that sits in the car factory and just is the robot arm that does the same thing time and time again. Building a robot that works with humans is harder. Right? An autonomous car, an autonomous vehicle is designed not to interact with humans, right? You want to stay away from humans with the car. A robot, you'd like it to interact. You'd like the robot to bring you coffee. So it's actually harder, the AI, for robotics to build a fully autonomous robot that interacts with humans. This is our little pet robot, Isaac, NVIDIA Isaac. And so Isaac drives around, rolls around our NVIDIA headquarters. If you're ever visiting Silicon Valley, please talk to EJ or one of the NVIDIA people and stop by for a tour, and you may see Isaac. It's a 2-story building, so Isaac actually goes up the elevator. We don't have a lot of elevators in the building. We like our employees walking up and down the stairs, but Isaac takes the elevator. And for Isaac, we use many of the same software technologies that we use to build an autonomous vehicle. You can't plan everything. So you can't have Isaac do everything in the real world, or it takes too long. Think if you want, and it isn't always safe. Think if I wanted to teach a robot to play golf, right? You don't want that robot practicing next to your house where there's some windows, right? You want it to practice in a safe place. And the safest place for a robot to practice is inside the computer, in a simulator. So on the left, you see our Isaac simulator. And of course, when it's inside the computer, you can not just model one Isaac, but unlimited numbers of Isaacs. So every Isaac has a GPU in a server, and Isaac is trying to figure out in a simulator how to put a little round cylinder inside a round hole when you have a round, square, and triangle hole. And all of the laws of physics, of course, using high-performance computing are modeled. So all of that work that we've done with CUDA over the last 10 years and HPC and physics and other fields is now being applied to robotics. And we can let now Isaac run in the simulator. It's super real-time speed. And then all of the robots exchange their deep neural networks. The best one then is moved to the real Isaac robot. So now here's the real, this is not Isaac, this is another robot, but it didn't work the first time, but let's see how many times it takes. That's not bad. The robot practiced millions of times in the simulator, and now just a few times in real life. So all of this software for Isaac is available as a software development kit. We make it available for you to build your own robots. And Naver Labs, right here in Korea, is building their own robot using a number of different NVIDIA GPUs and technology. So I'm sure there's other robotics companies or will be here in Korea, and we would love to work with them. So NVIDIA Hgx, the first embedded or edge platform for autonomous machines available now. And the development kit, NVIDIA Jetson Hgx, available as a complete kit to get started. So some great examples that we talked about from Korea, of Korean companies saving money, delivering business value today with GPUs, doing things that they simply could not do with CPU computing because of the death of Moore's Law, the end of Moore's Law. And a complete lineup of new NVIDIA GPUs we launched this year, new platforms for inference and for machine learning, in an ever-growing ecosystem of all sorts of new machine learning and other partners. So with that ends my talk. But again, we started as a graphics company, and so some of our engineers had a little bit of fun with Turing and put together another little home video, a little bit more fun maybe than the self-driving car, a little bit different. And so I will leave you with that closing video.